So as usual, if you do not wish to appear in the live stream and recording, turn off your microphone and camera.
Oh, do I need to do that also on iPad? Oh, got it.
Okay, so welcome everyone to this week of this week's mini course by Yilin Wang, who is telling us about large deviations of SLE and Weil-Petersson Teichmuller spaces. So we will have the usual 3 lectures, Monday, Tuesday, and Thursday at this time. And Yilin, please.
Thank you very much for the invitation. And thanks also for providing this platform for having those accessible lectures. And yeah, I'm glad to see you all here. So my lectures would be about large deviations of SLEs and some connection to maybe a less familiar object called Weil-Petersson Teichmuller space. So I won't assume you know either SLE nor Weil-Petersson Teichmuller space. I would just try to give you an idea what they are, how they're related. Maybe even just to fit you inside a bit of the background and situate you how is in the whole picture. That SLE, full name for Schramm-Loewner evolutions, they're families of random planar curves without self-intersection. So they're totally probabilistic objects. And if you look into SLEs, you will see the tools that people use are from stochastic analysis, where you see martingales, the Sanov theorems, and Bessel processes. And they were introduced to describe conformally invariant 2D static mechanics model. So by conformally invariant, conformal, we will hear a lot of things about conformal mapping. So this is notion from complex analysis. Conformal mapping, we only talk about 2D conformal mappings. These are angle preserving mappings. But if you just use complex number to represent those conformal mappings, those are just biholomorphic functions. They're holomorphic and their inverse is also holomorphic. They're always biject too. And SLE, they're motivated by studying those conformal invariant 2D static models, like spin models, and looking at interfaces in those models. And sometimes you also hear talks about SLE that are related to scaling limits of random planar maps. There's also a kind of discretized version when you take the mesh size going to 0, you see some random curve appears like interfaces. And also connection to 2D Liouville quantum gravity, and also connections to conformal field theory. The connection to conformal field theory is quite vague, as people even don't know what conformal field theory would mean. Like people don't really agree on that, but they're closely related to those conformally invariant to these static mechanics models. So these are sides of SLE, and Weil-Petersson Teichmuller space. They're deterministic objects, and keywords like quasi-circles. So these are some kind of Jordan curves. They're under image. Their image of circle, round circles by quasi-conformal mapping. So quasi-conformal mapping is kind of a less, it has a bit less restriction than conformal mapping. For conformal mappings, they send infinitesimal circles to infinitesimal circles, but quasi-conformal mapping, they will send infinitesimal circles to ellipses. And the objects, like the field which study those quasi-conformal mapping and quasi-circles, also studying those conformal mappings, called the geometric function theory, where we study property of the curve with respect to property of conformal mapping to one side of the curve, for instance. And Teichmuller space usually refers to complex structures on Riemann surfaces. You maybe have heard about moduli space, Riemann's moduli space, and Teichmuller space is one way to describe it. And geometers or analysts usually looking at those Weil-Petersson Teichmuller space, they care about the structure on those space. So if now you can think this Teichmuller space as a space of conformal structure or the space of quasi-circles, a space of quasi-circle will be infinite dimensional space. And they care about the structure, which means that what does it mean to take a derivative in this infinite dimensional space? What does it mean to measure how far two quasi-circles are from each other? What is the distance? And what is a complex structure? How can you turn 90 degrees? And what does that even mean? And so all this, they study more this abstract side of the geometry of the whole space of quasi-circles. And this is for here, the Kähler geometry. And from physics side, they're also related to string theories. And physicists they really care about those Kähler geometry of space of closed curves. So you can see that these two fields are totally, they have different tools and they care about different problems. And there was not so many connection between them before 2018. So my talk here will be telling you that these two guys are actually closely related by this thing called Loewner energy. So the Loewner energy will be coming from large deviations of SLE, and that will also relate to the Weil-Petersson Teichmuller space. So the first goal of my series talk is to tell you what this connection is. What is this Loewner energy? What are these SLE and Weil-Petersson Teichmuller space? And in my third lecture, and so that will be also focusing on how can we get results for Weil-Petersson Teichmuller space from SLE, vice versa. How can we get conjectures from non-result on this column to result of SLE? So here is the plan. So for today, I will really start slowly with telling you what is Brownian motion and how that related to Dirichlet energy, what is SLE, Loewner energy, and at the end tell you what is the large deviation result that we have. And for tomorrow, we will talk more about this Weil-Petersson Teichmuller space. And for that, we will generalize first to a loop energy. So we will talk about energy for chord today. And on Thursday is focusing on a particular example of how results from SLE, from random conformal geometry, would inspire results for Weil-Petersson Teichmuller space. And many of my other works that I won't be talking about is always spinning around this idea of I know something about SLE, and I know a lot of people working on SLE and try to translate the question or the results from SLE world to the side of Weil-Petersson Teichmuller space. And sometimes I can use this relation between SLE and Weil-Petersson Teichmuller space to prove results on the right-hand side. Sometimes I would just guess to conjecture what should be the theorem and then prove it directly on the deterministic side. So you will see examples of that in the series of 3 lectures. But yeah, if you have questions, please feel free to interrupt at any time, and I'm happy to answer. All right, let's just start from Brownian motion. And here I show the one simulation of Brownian motion. I just was lazy, and so I just picked from Tom Kennedy's website. This is a Brownian path. So one way to characterize Brownian motion is by its universality. And we say that Brownian motion, or more precisely, multiple of Brownian motion, are the unique continuous random processes which would satisfy W0 at time 0 equal to 0, is centered, its expectation is 0 all the time, and has independent and stationary increments. All right, that means that if you take finitely many time points, and the increments of this path is independent family. Moreover, the increment has the same distribution as if I just take the time difference, evaluate at T1 minus T0. And here, just with these 3 properties, and also that is continuous process, it gives you that for a fixed time t, the distribution of Wt has to be a centered Gaussian random variable. So here, this kappa is a number that is the same here. So, and the density of this finite dimensional marginal that all of you know, that will just be taking the product of each of the increments, the density of the increment. And here, the variance is on the denominator. So here is just one illustration of, like, we are very familiar with that. With very few axioms, I will already single out the important role of the Gaussian variables and also the universality of Brownian motion. And that's why Brownian motion, there are scaling limits of simple random walks, etc. Right, physicists, they also look at Brownian motion, and they would write this path integral that says the density of the square root kappa b is given by exponential of minus I of W. This is, I will call this is the Dirichlet energy of W divided by kappa multiplied by a Lebesgue measure on space of continuous function. All right, so there's a lot of issue here, but it still kind of makes sense. Here we look at the finite dimensional marginals, and you can see that it will take the product of this increment square divided by the variance. And if I take the point, you sample more and more points, then what I will have to see here, it will be 1/2. So there will be a kappa here, and we'll just take out the 1/2 here. And 1/2 times supremum over the sum of this increment squared divided by time increment. And after taking the supremum, this is exactly 1/2 of the Dirichlet energy of a function W. All right, let's first assume that Brownian path has Dirichlet energy. So that what this Dirichlet energy means is that if W is absolute continuous, then you can take this derivative, time derivative, almost everywhere, and you square it. And this is the Dirichlet energy. Right, but unfortunately, Brownian motion doesn't have finite Dirichlet energy. So almost surely, Brownian motion has infinite Dirichlet energy. So this doesn't really make sense. But also, this Lebesgue measure on space of function, that doesn't really make sense either. But however, this would be a like reasonable approximation if you talk about this finite dimensional marginal, for instance. So physicists call this Dirichlet energy to be the action functional of Brownian motion. And more generally, there are many ways mathematically rigorously make sense of this action functional for infinite dimensional space in the Gaussian measure on infinite dimensional spaces. So I will focus on the particular version of that is called the Schroeder's theorem, which is describing some asymptotics of when kappa goes to 0. So intuitively, that would mean that the probability of this square root kappa b, when kappa is very, very small, to stay close to a given deterministic function W, its probability, unless W is the constant function 0, then this probability, otherwise this probability will be extremely small. And it is small, it decays very fast, like exponentially decay when kappa goes to 0. But here the rate function is exactly the Dirichlet energy of W. So this is the same expression as here, but it was only about kappa goes to 0 behavior. And more precisely, the large deviation results that for the Brownian path is that if you take any fixed time, finite time, then the Brownian motion restricted to this finite in time interval is a random function, is a continuous space of continuous functions starting from 0. And I will put the subnorm topology, and that means that for any Borel set inside the space of continuous function, the probability of the square root kappa b belonging to the interior of this set, you take log multiplied by kappa, it will be larger or equal, you take lim inf when kappa goes to 0, or larger or equal to infimum of the Dirichlet energy for all the W inside this interior. And this inequality here, this is a trivial inequality because I'm just replacing interior of A to the closure of A. And this is larger. And now I also switch to lim sub. But then the other part of the large deviation result it says that this supreme, the lim sub of this quantity is bounded from above by infimum of the energy, Dirichlet energy for W inside the closure of A. All right, so why I say this is the intuition that you can have in mind is that if you take A to be an epsilon neighborhood of W, then the right-hand side here you will have, instead of the Dirichlet energy of W to be the infimum of the Dirichlet energy of W inside this epsilon neighborhood. And one other, we always ask this rate function, this I would be called the rate function of I, that is lower semi-continuous, which means that if you have a sequence of function that converging for this topology, then the lim inf, it will be larger than the energy at the limit. So if you take epsilon go to 0, here it will go to the function itself.
Yeah. Sorry, and there is a question in the chat.
Yeah. So what is the motivation? Square root kappa of B. So for me, I will talk about large deviation of SLE later when kappa goes to 0. But here what we do is to study some extreme rare events about Brownian motion doing certain things. So when you take kappa very small, the square root kappa times B, it is, if you ask it to stay close to W, so it's a very rare event, and it's somehow telling you how study of the rare events of Brownian motion. Yeah, so I don't know if it's answer your question. Can you hear me?
I hear you fine.
Oh, yeah. So I can also repeat the answer. So here, the motivation to study square root kappa of B is to study some rare events of Brownian motion. The whole idea of large deviation is to study rare events and how rare those things are. Like for instance, here it will tell you that if the Dirichlet energy of W is large, then this probability is really, really rare. And how rare it is will depend on the Dirichlet energy. So it is kind of so the whole story about large deviation is to study those rare events. Okay, thanks for the question. Yeah. All right, so that's the terminology that lower semi-continuity, that means it's like this. But here we have something more, is that this I is good, which means that the sub-level set, so you look at all the function which is below, whose energy is less than L, is compact. And when this condition is there, is sometimes it's more easier to carry out a lot of resulting large deviation later. So one remark here I want to emphasize is that large deviation is not only about the distribution of the function, but it's also about the topology that you can put on the space. Here I have to look at the interior, I have to look at the closure. So they all depend on topology. Here the lower semi-continuity is about topology. The compactness, it also depends on topology. So, and here also I need to take the time to be finite so that the topology would be the sup norm. But actually we can also take the time to be infinite. Then the topology we can take is the uniform convergence on compact sets. So this is called the shoulder theorem. It's about large deviation of Brownian motion. So if you just ponder a little bit, like the story about Brownian motion, it starts with this universality property. This is the unique process which is doing blah, blah, blah. And that will single out the role of Dirichlet energy. If you just talk to a function analyst, like they will tell you, okay, Dirichlet energy, they was giving you the simplest example of Sobolev space, is a W12, and but however, probabilistically, it has a meaning. It will just coming from very simple axiom. It will tell you Dirichlet energy plays a special role there. All right. So this is the basic things. The motivation of Schramm when he introduced Brownian motion is that this question about how first we can definitely generalize Brownian motion to higher dimension, which is taking 2 copies. So 2D Brownian motion will be 2 copies of Brownian motion that are independent, but it will be a Markov process. So it will forget, it doesn't know where it has visited. You just keep going visit itself infinite many times. But what if you ask for a random planar curve without self-intersection? How can you describe such curves? And why do we care? For instance, from 2D second mechanics models, for instance, here you see a simulation of easy model. I'm not going to define it, but you can just see that there are 2 different colors, the minus spin and plus spin. And if you force the boundary to be minus here and the boundary to be plus here, it will force the interface between the 2 clusters. And at criticality, there's a temperature in the easy model. At the critical temperature, this interface will have a conformally invariant property. That is, if you take the mesh size going to 0, you will see some macroscopic, there one curve like this, but this curve is a random curve. But if you just multiply the square by 1/2, say again, you like squeeze it a little bit, or you zoom in a little bit inside, the curve will have the similar law as before. This is conforming invariance. But here it was just very general idea that how would you describe this interface? If after taking the mesh size going to 0, it will be a continuous, a curve without self-intersection. So actually, it might touch itself in other models, but they can never cross itself. As an interface, they will never do that. So Oded Schramm introduced SLE to describe this type of interface. And he actually used the so-called Loewner transform. Actually, he has just invented it again himself, and then realized that, okay, Loewner already invented that 80 years ago. So when Oded Schramm introduced, that was in 1999. So let's just see what is Loewner transform. So we will talk about a simple chord. It's a similar situation as here. A chord means you have a simply connected domain. You have 2 boundary points. The chord is a simple continuous curve from one boundary point, the other boundary point. And because of Riemann mapping theorem that says that any simply connected domain with at least 2 boundary points can always be mapped to the upper half plane and sending one point to 0, the other point to infinity. So we just look at the case when the simple chord is in H, the upper half plane, and I also put the 2 boundary points, this starting point and this is the end point. So the chord will be viewed as oriented curve. So to describe it, if I have this simple chord, I parameterize it in a so-called capacity parameterization. What is that? So you look at the initial bit of the curve, and then you cut it. The complement of it, this gray shaded area, is simply connected domain. And you can map by Riemann mapping theorem. There's a conformal map GT that is sending this green part to the upper half plane again. And there are many choices, but we choose the normalization at infinity such that it's conformal map. Its expansion at infinity is just the identity map. So the next term in the expansion should be a constant term, and you ask it to be 0. And the next term here, all the rest, they are going to 0 when z goes to infinity. But here, this number, this is a positive real number. It will measure how large this size is. This is called the capacity of this part of the curve that you map out. And we choose the parameterization of gamma such that this number here is exactly 2t. So this is parameterization. It comes together with the curve. Once you know what is the set of the curve, then you know how the parameterization is. And after parameterization, I just call this conformal map GT. And the tip will be sent to some point on the real line. And the image is called WT. And now this is a function starting from 0, continuous function. And this is called, as a function of t, this is called the Loewner driving function of gamma. All right, if you have a curve, you can write down this real function W. And we can actually also recover gamma from W. So W, you can determine gamma. I will come back to it later. As an example, if you have this curve from 0 to infinity, like just straight up, the mapping out function will be this square root of z squared plus 4t, and you can check the expansion is exactly this form. And what it does is really cutting this orange curve here and split it into 2. Now the WT has to land at 0. So this driving function has to be 0 because of the symmetry. It's always 0. So if when the driving function is 0 all the time, then the curve is just the straight up. All right, some properties about this transform. The first is additivity. So if you look at the curve, if I fix t, I map out by gt. I look at this curve, orange curve remainder here. Now starting from WT goes to infinity. And if I translate back by WT, I get another curve starting from 0. Its driving function will just be the increment of the original driving function. Next property is the scaling property. If you multiply your curve gamma by a positive number lambda, then the driving function will change in this explicit form as the Brownian scaling. So the remarkable thing is that Brownian motion is invariant under these two transformations. And I already mentioned that we can also recover gamma from the driving function itself. Actually, now as a function of t, this gt of map, if I take a z belonging to the upper half plane, it will follow this differential equation. It starts with identity function as starting from z, and it will follow this differential equation here. So this is a vector field which will depend on where WT is. And I just write down this vector field, how it looks like. It's a singularity around WT. And the vector field was pushing away from WT. So how can we recover gamma from WT is that you just solve this. If I'm given this WT, and I just solve this differential equation, and there is this singularity from the vector field, it's going to attract a lot of points just above it. And WT is a continuous function which has been moving on this real line. And this differential equation is only well defined if the point hasn't hit the flow doesn't hit the singularity. So this differential equation will be defined on a subset of the upper half plane, and which is exactly outside of gamma of 0t. So if your curve, like here, this will be the set of points where this differential equation has exploded before time t. This is also consistent with the fact that GT is only defined in the complement of the red part. So you can keep this idea in mind that what is this driving function doing? You can think a very powerful vacuum, and it's moving on this point is swallowing the points above it and pushing the points towards left and right. And if you're away from the point, the vector field is really small, it affects very little, and keep opening up the upper half plane. And you can recover the curve gamma by looking at where are the point where the solution doesn't exist. All right. So this way, you can also define for an arbitrary continuous function W. So here all I say is that if W comes from gamma, then you can recover gamma this way. But if you start with an arbitrary continuous function W, then HT is still well defined, but now KT would be the complement, should be here. The KT is the place where the solution is not defined, but KT does not need to be a simple curve. So in the end, what you get in general is a family of decreasing simply connected domain HT, or a family of growing house of KT. And this HT, they always contains the neighborhoods of infinity. Schramm then says that, okay, let's use this, and by just looking at the Loewner chain, so this is called the Loewner chain, the family of HT, or the family of KT, or the family of GT. So there you can determine one each other. And this SLE is the Loewner chain driven by square root kappa times the Brownian motion. And when kappa is between 0 and 4, this curve is almost surely a simple curve. This is highly non-trivial result of this phase transition, that when kappa is between 4 and 8, it's still described by a curve, but it will be self-touching, and KT will be the set that is filled in inside here. And when kappa is greater or equal to 8, there's a random curve that is space filling. And here is a simulation. It's using the same Brownian path of Tom Kennedy that shows that. So here he only draws the curve here, the orange curve that I drew. And for KT, you have to fill in all these bubbles, which when the curve touches itself. So you can see that when kappa is small, the curve is a bit straighter. And when kappa getting larger and larger, it gets more and more fractal. And when it gets larger than 4, it's even touching itself. When kappa is greater than 8, it's filling this whole space. All right, so that will depend on kappa. And in my talk, I will be especially looking at the case when kappa is very small, when kappa goes to 0. And SLE kappa inside another simply connected domain from A to B would be the pullback of SLE kappa in the upper arc plane by a conformal mapping phi. So here you have a phi is a conformal map from D to upper arc plane, sending A to 0, B to infinity. On the right-hand side, you know how to define an SLE. And the SLE in the domain on the left-hand side will just be the pre-image of this curve. So here, this map is not unique because we can also multiply by another number on the right-hand side, by a positive number. But however, because of the scaling property of the Loewner driving function, the driving function changes exactly as the Brownian scaling, and Brownian motion is invariant under that scaling. So SLE is well defined, even though we didn't tell you which phi that we choose. We only ask A to 0, B to infinity. Why people care about it? Well, we see the universality of Brownian motion, and those very simple axioms for Brownian motion, they will translate to SLE. So SLE are the unique random process of non-self-intersecting curves, which would satisfy, first of all, conformal invariance. That means if you have as defined SLE from this domain from this point to this point, and there's also SLE in the square from this point to this point, and the law of this curve would be exactly the image under a conformal map from the curve here. It's just coming from the definition. We define SLE to be conformally invariant. But what is not clear is that so what is non-trivial is that this curve is also invariant under scaling here. So after checking its invariant and scaling, it's automatically conformally invariant. The next property is called domain Markov property, which means that if I explore my SLE already up to time t, the remainder of the orange curve it's an SLE in the complement of the first bit. And that is, which says that just coming from the fact that the Brownian motion has independent stationary increments. And the magic of the SLE being the interfaces in static mechanics models, say like critical easing, Gaussian free field, critical percolation, scaling limits. The magic actually happens at those criticality, those scaling limits has these two properties. But once you know they have these two properties, then automatically they will be one of the SLE. And then you only need to determine which kappa it is. All right. So Loeffler energy. Well, we have seen Brownian motion is related to Dirichlet energy. Now, Loeffler energy is defined to be the Dirichlet energy of the Loeffler driving function. Or if you have a curve, deterministic chord from 0 to infinity in the upper plane, I just define the Loeffler energy to be this way. So if the driving function is not absolutely continuous, then you just take this to be infinite. So this Loeffler energy is a number between 0 and infinity. There's some subtlety about what is total capacity. When the curve goes to infinity, the capacity doesn't need to be infinite. But in the case where the curve has finite Loeffler energy, then this capacity is always infinite. So you can just think of capacity always being infinite. So this you can replace this integral from 0 to infinity. And we can also similarly define the Loeffler energy for gamma inside other simply connected domain by just mapping this curve to the upper half plane and saying the Loeffler energy of gamma is the Loeffler energy of phi of gamma. Well, here again, this phi is not unique, but we can check that actually if you apply a scaling to phi, then the Loeffler energy doesn't change. So this is already not surprising because of Brownian motion is invariant. Its law is invariant under the Brownian scaling. And Dirichlet energy is its large deviation rate function. But we can also just check it directly. So the driving function of the scaled curve is just lambda times w at time lambda to the power minus 2 times t. And its Dirichlet energy would just be you taking its time derivative. Here you will pick up a lambda to the power minus 2, and lambda becomes lambda inverse. And after a change of variable, here you will just find out this is the Dirichlet energy of the original driving function. So the definition of the Loeffler energy doesn't depend on which phi that you choose. All right, and for the additivity, what that says is that you can just look at this picture. If I have the curve from A to B, let's say if I stop at time capital T, then I can compute this Loeffler energy of this curve by summing up the Loeffler energy of the first bit plus the Loeffler energy of the second bit, but in the complement of the first one. And this is coming from the domain Markov property. But directly from the driving function, what I do is just simply write this integral of the Dirichlet energy, ws dot, just split it into the sum of two integral from 0 to little t. So this will be this Loeffler energy. But this guy here from little t to capital T, that is also the derivative of the increment of the driving function. Right, so this is the driving function of this curve, this little bit of curve, but in the complement of the first one. Right, so here we write that Loeffler energy from DAB is the original one up to time little t, and now the new domain will be the complement of the first bit, and starting from gamma T and heading towards B. Conformal invariance discounts for phi because it's defined to be a conformal invariant guy. Another remark is that the minimizer of this Loewner energy. Well, in the upper half plane, what is the one driving function which would minimize this curve, this energy? Would be the driving function is constantly 0. So that was the curve which is going just straight up. And if you want to give a fancy name to it, it's the hyperbolic geodesic. So for each simply connected domain, there's a hyperbolic metric where between any two boundary points, there's a unique geodesic. And here from 0 to infinity will just be this straight line straight up. The hyperbolic metric, this is using this term because this is a unique metric that is invariant under the conformal automorphism of the domain itself. But if you like this hyperbolic geodesic, it just means this line that's from 0 to infinity straight up. On the left-hand side, this hyperbolic geodesic from A to B is just a pre-image. Right, this. So it's a curved, it's just pre-imaged by phi of this straight line. This is what I meant by hyperbolic geodesic. Or you can just say, well, this is SAV 0. The driving function is 0. Another example is that if you look at this curve in the upper half plane, which is this ray starting from 0, making an angle theta, when theta is not pi over 2, then this driving function will be a constant which depends on theta multiplied square root of t. And this driving function, you take its derivative, you get 1 over square root of t, you square it, you get 1 over t. It's not integrable. Right, so this curve has infinite Loewner energy. And this tells you also that if the curve is making an angle, well, and making an angle, then if it's making an angle at gamma t, then if I open up this slit, and it will be mapped, this slit will, the two sides of it will map two sides of the tip. And here there will be an angle here, which won't be pi over 2 if here this angle is not pi. Right, so whenever the curve has a corner, then the Loewner energy will be infinite. Because this part has infinite energy, then this curve, its energy will be the energy of this orange part plus the energy of this red part. This is infinite. So there are a few examples. So finally, this is the result I want to show you. That is the SLE 0 plus large deviation. And this has, so this version, there's another version of, but I will just present the newer one that is a joint work with Evelina Pertola. I mentioned that to talk about large deviation, we will need to specify which topology we talk about. So I will sit inside the unit disk and I look at curves going from -1 to 1. I will endow the space of curves with the Hausdorff distance. The Hausdorff distance, I just remind you that it's the smaller epsilon such that k tilde is included in epsilon neighborhood of k and k is included in epsilon neighborhood of k tilde. Right, so the random curve, the SLE kappa will be a random curve. So this will be a random element in this space for small kappa. Anyway, we're looking at kappa equal to 0 behavior. So it satisfied large deviation principle with good rate function, the Loewner energy of the curve here. All right, so again, like just remind you what this large deviation would mean is that for very small kappa, SLE kappa would like to stay close to the geodesic from -1 to 1. And that is just a straight line in the unit disk from -1 to 1. But now if I'm giving you another curve gamma from -1 to 1, and this is curve is drawn in orange here, the probability of SLE kappa stay close to it is very, very small. Right? But how small it is decaying like the Loewner energy of gamma. And you can, it's totally similar to Schroeder's theorem, and it's also actually consequence of Schroeder's theorem. But what is technical, there's a lot of technical difficulty is that this transformation from the driving function W towards this set of simple curve, so here to make it well defined, I have to take W to the union of the halves and take the closure so that it becomes a compact set. This is not a continuous map. Actually, for a large deviation, if you have a continuous map, then also the large deviation is not hard to transfer the large deviation on the beginning part to the image part. But here, this map from the driving function to the curve itself, especially when it's endowed with the halves of distance, is not totally, it's not continuous at all. But so these are some technical difficulty, but in the end, the result itself is just a consequence of the Schroeder's theorem, where it says that I know how the real events of small multiple Brownian motion are like, and then it will tell me something about small kappa SLE, how that is related to Loewner energy.
I have a question. In the picture, you say that gamma wants to stay close to the geodesic. Is that the hyperbolic geodesic that you mentioned before?
Yes, that is the hyperbolic geodesic.
Thank you.
Yeah, that is in the upper half plane, this zero driving function, so that is curve going straight up. Yeah.
Thanks.
Okay. All right. So some remarks is that it doesn't really make sense to talk about the Dirichlet energy of Brownian motion. So it also doesn't make sense to talk about what is the Loewner energy of an SLE curve. Maybe to illustrate it more is that if you have a driving function with finite Dirichlet energy, then it's automatically Holder 1/2 continuous. And to check that, you look at the difference of the driving function. I just write from S to T of the time derivative of the driving function. Then I use Cauchy-Schwarz. It gives me square root of T minus S multiplied by square root of the integral of WR dot squared. Well, this guy here is bounded by 2 times the Dirichlet energy of W. So this is telling you that the increment is bounded by its Holder 1/2. And actually, even we can say more that when T goes to S, this constant here is going to go to 0. So it's actually even stronger than Holder 1/2. But you also know that Brownian motion is only Holder 1/2 minus epsilon. It's definitely not Holder 1/2. So it doesn't make sense to talk about Dirichlet energy of Brownian motion. And so here you see that the finite energy driving functions is more regular than any Brownian motion. And also for the Loewner transform, so this square root of kappa B, you give you SLE kappa, and it was shown by Bafara that it has halves of dimension 1 plus kappa over 8. Right, when kappa goes to 0, this dimension goes to 1. And when kappa goes to 8, this dimension goes to 2. That's also fit together with the fact that SLE becomes space filling when kappa is greater than 8. But for finite energy curves, they were shown to be rectifiable. And being rectifiable, it means that you can compute this length by sampling more and more points on it, you look at what is the chord length between the two points and sum them up, and this primum exists. This is rectifiable. So it's also fit together with this when the house of dimension goes to 1. And it's a rectifiable quasi-chord. So it's another type of a chord. It's in the quasi-conformal mapping. I will talk more about it tomorrow. And this is a result by Fritz and Shekhar, and they have been looking at the Loewner transform of functions with finite Dirichlet energy, and they show that. So you can see again this finite Loewner energy curve. They are more regular than SLE kappa. So it's really capturing some behavior when kappa goes to 0. It's asymptotic behavior of SLE. But on the other hand, if you think about how Dirichlet energy is the action functional of SLE, of the Brownian motion, you can still think of this, although it's telling you some asymptotic behavior, it still captures information about SLE. So it should be, if the physicist notation of this density is given by exponential of the Dirichlet energy, then it's actually telling you the law of Brownian motion is totally determined by the Dirichlet energy, or here we could imagine that Loewner energy totally determines the law of SLE. So this is something that is heuristic, and also I don't have any way to really make precise this idea, but so we will just be looking at, if you know something about SLE, what you can say about curves with finite Loewner energy. It just pose this as an interesting question, that if you know something about Loewner energy, can you say something about SLE? Coming back to that. And I don't know that. All right. The last consequence of this large deviation result, and I will show you, is this energy reversibility. You have a curve gamma in D from A to B. I can view this curve. So the curve is oriented. If I view this curve in the opposite direction, it will be a curve from B to A. I will write R to gamma R, this to reversed. And the Loewner energy of gamma is equal to the reversed curve, the Loewner energy of the reversed curve. This is a totally deterministic result. In the upper half plane, that means if you have a curve gamma from 0 to infinity, if you apply -1 over z, which will swap 0 to infinity, then this curve, you start from this blue part and follow with the red part. They have the same Loewner energy. But this is a totally deterministic result, that you have this curve, you can write down its driving function. You reverse it, you get another curve, you try to write down its Loewner driving function. You check their Dirichlet energy should be the same. But however, this deterministic result is very hard to prove if you only know what I told you so far. The reason is that when we define the Loewner driving function, say, what is the driving function at this point? It will depend on how the conformal map of this red part is, right? You have to open this part, you fix infinity, you have to open up this red slit in order to tell where this tip lands on the real line. So it depends on the red part, but after inverting it, it will just depend on the blue part. So this dependence is totally exchanged, and it's very hard to write down what is driving function, how this driving function is related to this driving function. And it's very hard to do like deterministically. You will see another deterministic proof by, I will tell you an equivalent way to write down this Loewner energy. Then the reversibility will be clear. But so far, it's not so clear. So the first proof of this result, we use this idea from SLE. Right, this is the first example of how results from SLE will give you results about Loewner energy. SLE kappa is reversible. This is a very impressive result that is proved by Jan and Miller-Sheffield. So this holds for kappa between 0 and 8. Well, it's reversible. What does that mean? Is that as a curve from one point to the other boundary point, if you view it from the other direction, it will be have the same law. All right, that is natural if you know that SLE kappa, at least for some fixed kappa, it will be the interface in the easy model, say. That interface don't have a direction. Like you don't know which way you go. So it has been conjectured and finally proved by Jen and Miller-Sheffield. Right, so then we can use the large deviation result. Here's the heuristic proof that we can make sense easily, that SLE kappa stays close to gamma in DAB. So SLE kappa in DAB stays close to the curve gamma from DAB. Is exactly the probability of the reversed SLE kappa stay close to gamma reversed in DBA. This is a tautology. Well, okay, so here the staying close is the Hausdorff distance. And that's why we actually really want to make the harder version of large deviation principle in order to have more geometric distance on the space of curves. And using the Hausdorff distance, then this first identity is the tautology. You just reverse everything. But because of the reversibility of SLE kappa, so then this SLE kappa has the same law as the SLE kappa itself. So SLE kappa stay close to the reverse gamma in DBA. And this first probability, it has the asymptotic expansion when kappa goes to 0 of the minus the Loewner energy of gamma from DAB. But for this one, we get the energy of DBA for the reverse curve. Right? Yeah, just in short, that SLE is reversible, so its large deviation rate function should be also reversible. And you get this result. So this is everything I want to say. So for tomorrow, I will first generalize this caudal energy to loops, which will be even more symmetric object. And here you have still two boundary points, and you will see even more symmetry in the Loewner energy, and then that will relate to the Weil-Petersson Teichmuller space, etc. And in the last lecture, I will show you how one can deduce one side from SLE results to results on the Weil-Petersson Teichmuller space. Okay, thank you for your attention. Yeah.
Thank you. So let us all unmute and thank Yilin for this first lecture. And I will stop the